So you could probably answer a lot of the note questions from 1.5 by yourself. We've already learned a lot of the content in 1.5. So I'll be asking for your help. Help me fill in some of these notes. Basically, up until this point, if you looked at the homework from last class and the class before, if we're approaching a vertical asymptote right now, we can't really describe what the left and right hand limits are doing unless we type it into our calculator. You all agree? Right now you're like, okay, I know I'm approaching a vertical asymptote. The overall limit doesn't exist, but what am I going to write for the left and right hand limits? I don't know. Let's type it in the calculator and see. Okay, that's what we were doing up until this point. So in section 1.5, what I do is I'm teaching you an algebraic way to get whether the right and left hand limits are going to infinity or negative infinity without using your calculator. So that's the whole purpose of section 1.5, day 1. We're going to be looking at limits as x approaches a vertical asymptote. Let's just start off by answering the question, when does a function have a vertical asymptote? If I give you a function on a piece of paper, looking at that function, how do you know there's a vertical asymptote? Lauren? Beautiful. When there's a factor in the denominator that doesn't cancel. I need to figure out what makes that denominator equal 0. Right? Whatever is going to make that denominator equal 0, that's going to tell me where my vertical asymptote is. Okay, so that's what I'm going to write. I'm going to say we're going to start by factoring and canceling. Right? You want to get this function as simplified as possible. You start factoring and canceling. Then we use the factors, or just factor, depending on how many are left in the denominator. To find the x value that makes the denominator equal 0. We look at the factors in the denominator that don't cancel with anything in the numerator. That's going to tell us where our vertical asymptote is, or vertical asymptotes. Okay. Factors that do cancel, what does that indicate? A whole. Okay, so if the factor cancels, it's a whole. The factors that are left over in the denominator that don't cancel, those are your vertical asymptotes. What type of continuity is found at a vertical asymptote? Very good. Non-removable discontinuity. Yep. Non-removable discontinuity is found at a vertical asymptote. If a function f of x approaches a vertical asymptote, the limit does not exist. Right? The overall limit does not exist as we approach a vertical asymptote. However, you are still going to describe the behavior of the left and right hand limits. Right? We talked about that. How for right and left hand limit, I never want you to put does not exist. I want you to describe the behavior. So if we're approaching a vertical asymptote from the left or right hand side, I either want you to put infinity or negative infinity. Tell me what's going on. It says the behavior of the limit can still be described by using values of infinity or negative infinity. So here's the big thing to remember. If you have a constant, that's what c is, a constant, over a number that's really close to 0, it's a really small number, that's going to cause the graph to shoot up towards infinity. So let's say I plugged this into my calculator, 10 over 0.0001. What do I get when I type that into my calculator? Should be some big number. That would be 0.001, that'd be 100,000. Is that what that is? Okay. You could even choose a number that's even closer to 0. You could do 10 over 0.00001. Ooh. Right? If I have 4 zeros, then that's going to cause me to go to, what is that, 1 million? Is that right? Did I type that in right? And you can see that when you have a really, really small number in the denominator, it actually makes you shoot up exponentially towards infinity. Okay? Whereas if I have a number that's really close to 0 in the denominator that's negative, then I go to negative infinity. Okay, but the concept's the same. We're going to be using this today. The ideas of infinity and negative infinity, so that's important to know. That if you have a really small number close to 0 in the denominator, it's going to make it either go up to infinity or negative infinity. So in the first example, it says find the vertical asymptote. Someone tell me. Wyland, where would the vertical asymptote be for that function? 1. Excellent. And how we find that is we have a factor in the denominator. We set it equal to 0 and solve for x. So I'd add 1 to both sides. And I would get that we have a vertical asymptote at x equals 1. Find the value that makes the denominator equal 0. Now, if I'm approaching a vertical asymptote, because everyone agrees that the overall limit is not going to exist. If I was trying to find the overall limit, what I would do for a normal problem is I'd first start trying to plug in 1. So I'd get 1 over 1 minus 1. We get undefined, right? So the overall limit does not exist. Now, if the overall limit does not exist, what could be happening? Either a vertical asymptote or a gap. In this case, we're approaching a vertical asymptote. But I'm not going to write does not exist for my left and right hand limits. I want to describe the behavior. So if I'm approaching an asymptote, what are my only 2 options for left and right hand limits? Infinity or negative infinity, right? That's the whole idea. So I can't plug in 1. We just saw what happened when you plugged in 1. It doesn't really help much. So instead of plugging in 1, I'm going to choose a number that's really close to 1 from the left-hand side. So what's a number that's really close to 1 from the left-hand side, or smaller than 1? Maybe like 0.999, right? Choose something that's really close, but it's not quite at 1. Now, plug that in. 1 over x minus 1. Right? If I plug in 1 over 0.999 minus 1, I'm going to end up with 1 over negative 0.001. What happens if you have a constant over a negative number that's really close to 0? It's going to go towards negative infinity. I want you to check that. On your graphing calculator, type in 1 over x minus 1. I want you to graph that function, and I want you to look at the left-hand limit. As x gets closer and closer to 1, does it look like your graph is going down to negative infinity? You tell me. Is that what it looks like? Does it look like it's shooting down to negative infinity from the left-hand side of 1? Okay, so that's just, you only have 2 options. You know your answer as soon as you know you're approaching a vertical asymptote. Left and right hand limits are either going to be infinity or negative infinity. Really, I just need to determine if it's going to be a positive number or a negative number. Okay? So if I'm approaching 1 from the right-hand side, now choose an x value that's really close to 1 from the right-hand side. So maybe like 1.001. If you want to get real crazy, you could do 1.0001. Okay? But it really doesn't matter because we know our answer is either going to be infinity or negative infinity. So really, as soon as I see that it's going to be 1 over a positive number, I know we're going to choose positive infinity rather than negative infinity. 1 over 0.001, that's going to go to positive infinity. Any questions about that? Yeah.
So basically, if it's coming from the left, it's always negative infinity, or if it's coming from the right?
No, that's not the case at all. It could be different. In the next example, we're going to see when we're approaching the asymptote from both sides, actually both are going to go up to positive infinity. So you have to do this test to determine if it's going to be negative or positive infinity. Yep. Yeah, you don't want to always just assume that the left-hand side drops down, the right-hand side shoots up. It could be opposite. The left-hand side could shoot down, or I'm sorry, the left-hand side could shoot up towards positive infinity, and the right-hand side could shoot down. Yeah. Yeah. Good question. All right, so for example 2, same kind of deal. We've got this function, and we want to find the limit as x approaches the vertical asymptote from the left, and as x approaches the vertical asymptote from the right. Where is the vertical asymptote? Tell me where's the vertical asymptote? It is 3. Yep. What would make that denominator equal to 0? It's going to be at 3. So I need to find the limit as x approaches 3 from the left, and we want to find the limit as x approaches 3 from the right. And my function is 1 over x minus 3 squared. And most of the time when I start a limit problem, I just start by plugging in the number. So I'd start by plugging in 3, but you would end up with 1 over 0, undefined, overall limit does not exist. Why does the overall limit not exist? Either a vertical asymptote or a gap. In this case, it's an asymptote at 3, right? So if I'm looking at the left-hand limit, I automatically know that my answer is either going to be infinity or negative infinity as I get closer to that asymptote. Okay, so for this one, I know plugging in 3 doesn't do anything for me. So I'm going to choose a number really close to 3 from the left-hand side. So maybe like 2.99. You could even do an extra 9 if you wanted to get crazy. Okay. All right, if I plug in that, I would end up with 1 over 2.999 minus 3 quantity squared. Okay. We end up with 1 over negative 0.001 squared. But ultimately, what's happening when I'm squaring it? It's going to become positive. It's going to be 1 over a positive number that's really close to 0. Does it really even matter what that positive number ends up being? No, but I already know I only have 2 options. Either going to be infinity or negative infinity. So as soon as I know it's 1 over a positive number, my answer is going to be infinity. Okay. Same kind of thing down here. I'm looking at my limit from the right-hand side now. So give me an x value. Jackson, what would be an x value you could choose here? 3.01. Right. 3.01 is great. You could do 3.001. You could do 3.0001. Okay? But the whole idea is I'm just trying to figure out if it's going to be positive or negative. 1 over 3.01 minus 3 squared. Is it going to end up being positive or negative? 1 over a positive number. So it's going to go up to positive infinity. So this is an example where from the left and right hand side, they're actually both approaching positive infinity. Go ahead and put that in your calculator. So I'm going to type into the calculator 1 over x minus 3 squared, graph it, and see if that's true. See if as you go towards the asymptote at 3, if both sides are going up towards positive infinity. Is that what it looks like? Okay, so there you go. So this is a nice example. Now, even though they're both going towards infinity, would you write that the overall limit is infinity? No, the overall limit still does not exist. Even though these infinities match, the overall limit still does not exist. Okay, because when we're finding a limit, we're finding a particular y value. If you cannot define that exact y value, then the limit does not exist. Okay, infinity is just a concept. It's not an exact value. Okay. Use the function below to describe when a function has a hole and when a function has a vertical asymptote. Someone tell me, when are you going to see a hole? What happens? Boom. When a factor in the denominator cancels with a factor in the numerator. Hole. Right? Where am I going to see a vertical asymptote? When a factor in the denominator doesn't cancel with a factor in the numerator. Right? You could look at those factors that are left in the denominator. Okay, so when I'm describing this, I'm going to say that there's a hole if f of x equals g of x, or if f of x equals h of x. Right, that's where our hole is going to exist. Because if f of x and g of x are the same, then those would end up canceling. If f of x and h of x are the same, then those would end up canceling. That's where your hole's going to be. Okay. All right, for asymptote, I want you to write if g of x or h of x does not cancel with f of x, then set each factor in the denominator, equal to 0 and solve for x. Set each factor in the denominator equal to 0 and solve for x to find your vertical asymptotes. Or vertical asymptotes, depending on how many of them end up canceling. Okay. Any questions about that? Hopefully I beat it into your head enough now that if factors cancel, it's a whole, and if there's factors that don't cancel in the denominator, it's an asymptote. Okay? Hopefully we've got that by now. Okay. So in example 4, how do I find the vertical asymptotes in the holes? What do I need to do to that function? Factor it. You got it. Take this, your x plus 4 times x minus 2 over, this is the difference of two squares, a plus b, a minus b. Oh, hey, looky there. X minus 2's cancel. Let's go. So, Jack, where's my hole? Yeah, I have a hole at x equals 2. Okay. You're good, yeah, absolutely. I have a hole at x equals 2, and if you're not sure about how I got that, it's just because I'm taking the factor and setting it equal to 0 and solving. Right, add 2 to both sides, we get x equals 2. Okay, where is my vertical asymptote? Val, where's my vertical asymptote going to be? Excellent. Yeah, vertical asymptote at x equals -2. And that's because that is the factor that's left in the denominator that doesn't cancel. We just have to figure out what makes that factor equal 0. Please do not put +2. Okay? You've got to look at this factor and figure out what x value makes it equal 0. If you've got to write out all of those steps and actually solve for x, do it. Okay? Just don't make that mistake. Okay. So in example 5, it says find all vertical asymptotes, non-removable discontinuities, and holes, removable discontinuities in each of the graphs. Okay, so I'm going to have you guys just fill this in for me. Now, what would you say for the first one? Where is my discontinuity and what type is it?
That's a vertical asymptote at -1.
Beautiful. The vertical asymptote at x equals -1. So what kind of discontinuity is that?
Non-removable.
Got it, non-removable. Excellent. Okay. All right, looking at the second one, I would start by factoring this. The numerator does not factor, but the denominator does. It's the difference of two squares. Okay. Nothing's really canceling. Okay. So Kyle, how would you describe the discontinuity? Do we have a hole in our graph? Or number 2? Do we have a hole? Oh, which Kyle? You.
You said you.
Huh? Okay, so is anything or any factors canceling from the top of the box?
No, 2 holes.
No. Okay, so there is no hole. If nothing cancels.
No, I meant to say vertical.
Yeah, there's no hole. Okay, so there would be 2 vertical asymptotes. Okay. So where would my vertical asymptote be? Vertical asymptote at what makes this factor go to 0? -1. Okay. And what would make the second factor in the denominator go to 0? positive 1. Okay, vertical asymptote at x equals negative 1 and x equals positive 1. So what kind of discontinuity is that? Removable or non-removable? What is it? Non-removable. Non-removable discontinuities are vertical asymptotes and what else? Gaps. Yep. Okay, the last one, cotangent. I want you to think back to the quiz we had, where the last question on the quiz was that multiple choice question, where you had to figure out where the asymptotes were. Remember that? Basically, when we're looking at trig functions, the discontinuities are going to occur if you have asymptotes. So like sine and cosine, those are continuous functions. But when you are looking at cotangent, secant, tangent, those are all the ones with asymptotes. So you got to know where those asymptotes are in order to describe the continuity. Okay, so this is coming back again. So I'm going to make an XY chart just so that we can get an idea of where the asymptotes are occurring. I'm working my way around the unit circle. 1, 0, 0, 1, negative 1, 0, 0, negative 1. Okay. And I'm going to be looking at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. Tangent is y over x, right? So cotangent is x over y is cotangent. Right, so I'm going to be moving around my unit circle looking at the x over y. So Colin, at 0, what does your x over y give you? It's undefined. Yeah.
She's on good.
Yeah, at 0, it's going to be undefined. What does that mean if it's undefined? Graphically, what's that going to look like on our graph? Whole or vertical asymptote. What is it for cotangent? A vertical asymptote. Okay, that cotangent is the one that looks like this, where you got those things going on, right? We're going to see vertical asymptotes there. Okay, so then at pi over 2, what's my x over y? Colin, just go ahead and keep going for me. X over y?
0.
0, yep. At pi, what's my x over y? Undefined, At 3 pi over 2, x over y? 0, yep, and then 2 pi is going to be undefined again. Okay, so that tells us where all the vertical asymptotes are. Now the way I write this looks a little bit different than before. Before, when I specified domain, you told me what x could not equal. You told me what you had to restrict from the domain. So for domain, I would say that x can't be at our first vertical asymptote, 0. And then how much more would I have to add on to get to our next vertical asymptote? Pi, right? So it would be add on another pi unit. So we multiply by that by k, where k is an integer, right? K could be any integer. So let's say k was 3, then you would have 3 pi, right? Wouldn't there be another asymptote at 3 pi if you kept going, right? But that's not what I want to write here, because here I'm describing the continuity. So it's a little bit different. The way I would describe the continuity is this. I would say that there's a non-removable discontinuity, because it's an asymptote, at x equals pi k. K an integer. I ran out of space to write integer, but you can write out the whole word integer. Okay, but that's how I write it. Notice it's a little bit different. I'm not putting x does not equal. I'm putting there's a non-removable discontinuity at this x value. So you're telling me exactly what x value you have the discontinuity. Is that every pi?